traditional task of ray tracing is to take the screen, shoot from the viewer a ray through each pixel of the screen, and use those to determine an object. Additionally, we might have lights. If we want to light the object, then we would then cast a ray out to the light, see if that ray intersects anything. If it does, then just abandon it. If the ray hits the light without intersecting anything, then lighting is applied to that fragment. What I'm trying to get at is that this is sort of doing two things. We're shooting a ray once to get the object which the ray hits, which is visible, and then we're shooting a ray again to go to the light. But we can adopt a hybrid approach. I mean, we kind of already have a technique that does this, right? Standard OpenGL. Why not use standard OpenGL to get information about a scene, and then send that information to a Raytracer and use it to calculate more complex lighting operations. This session is pretty involved. For that reason, I'm going to sort of just take a high-level approach of the strategy and some of the problems that I faced. And as usual, link is in the description. Just let me know if you'd like me to go in more detail in any of these stages. So if we visualize the shaders as sort of blocks, I'm sort of using 3 shaders. I'll have a geometry pass. This is like deferred shading. And the goal of the geometry pass is to capture information about the scene, what we can physically see. Basically, we will pre-bake a render state for every pixel, because we know where the pixel is on the screen by reading the color buffer, and we can encode other information like the world space position and all of that. Let me go into that. So the geometry buffer sort of has, I'm using 4 textures to represent that. Within the first texture, we'll call this G0, G1, G2, G3. The geometry buffer is all the information which is written in the geometry pass. Have a look in my Python OpenGL series where I talk about deferred shading for more information on that. But anyway, each of these has a red, green, blue value. So for G0, we'll get the color of the pixel, which was hit, the unlit color, the diffuse color. We'll get the emissive for the next 3 attributes, and then the position in world space, X, Y, Z, as well as the normal. And I'm not using it at the moment, but any other information that we want that we can get from just rasterizing triangles. So if we were to run this, let me actually go back here. So I'll just go to my engine, and yeah, it's a lot of code, but anyway, we'll go to the render scene. Okay, so first of all, we update the scene with all the info, then we do the geometry pass. Let me just comment this out. Okay, so whoops, we're not going to ray trace, we're just going to do pure rasterization. Then we go to the draw screen, and instead of binding the color buffer, which is written by the Raytracer, we will bind G0. And the first 3 components of G0 are the diffuse color. So I'll just run this. And there we have it. See, so we're just writing the diffuse color and looks black, but remember, this is the hieroglyphs. Actually, if I go outside, oh, it's all black. Never mind. This hieroglyph stuff is just emissive. There's no diffuse there. That's why this stuff is black as well. But yeah, it's just the diffuse color. And then likewise, G2, the first three components there, no, the last three are the normal. So if we sort of bind the G2 texture, and then I go to, where are we? The frame buffer fragment. Because I want to pick out just the last three. So I'll go RGB. There. The last three. It's GBA. Oh. Okay, let's run that. So here we have it. It looks very funky, and the color here is the normal of each of the components. So for instance, red is the X component. See the difference? Here we have a positive red, and here we have sort of a lack of red. Blue is the Z, so here we're pointing up, we have a positive Z. Here we have sort of a lack of blue, which indicates a negative Z, and then green is, anyway. This looks very funky, as a matter of fact. We could make a whole game like this. Yeah, and here we have just the blue, which is sort of the just the default, like no color, no normal. Okay, so the point is, this is a rasterized pass, so it's doing the standard sort of stuff. So if I were to draw one of these triangles or a plane or something, okay, so here's my plane. If I were to do this in the geometry pass, I would have the standard, vertices, the VBO, VAO, vertex count, and all of that. So that's for my plane. And this stuff is the data used by the geometry pass. It's just standard rasterization. But then the next step is we ray trace. And in order to ray trace, we need a ray tracing description of the plane. So then we have the standard format that I've been using before. So we have like center, Umax, Umin, and all of that. That gets passed in separately. So we kind of have two representations of the same plane, but each of the shaders knows how to deal with it differently. And all the ray tracing shader is doing is it reads from the screen, and for each position on the screen, it has a render state, which has already been calculated that it gets by just unpacking textures. So if we go over to where are we? The Raytracer shader. We look up at the top. And actually, no, let's look at the first pass code. Okay, so we know the pixel coordinate on the screen that we are at, and we can get the render state by unpacking that. And all that's doing is it's reading these four textures and just reading the data from there. So again, this code already calculates the world position that the ray hit the object at, and it already calculates the color of the unlit texture and all of that. So we have that, we're good to go. All we need to do is light it, and that's what this Raytracer is doing. So it's actually very sort of minimal compared to what it was doing before. It just takes a pixel, takes a render state, and then performs the calculations to light that render state. But making this shader more lightweight is actually really good, because when it's doing a heavy computational load, it's slow. Yeah, and then this Raytracer, its job is to sort of fill up a color buffer, and then that color buffer goes to sort of a screen shader that just draws all of that as a rectangle on the screen. And if we want, we could throw on post-processing effects or whatever. But anyway, that's our hybrid approach. So let me just revert that. Okay, so again, we'll run through this. We update the scene, that is, we grab all the data and we write that in. Then we render with a geometry pass. Then we render with a ray trace pass. Then we draw the final result. In the geometry pass, we prepare all the data that needs to go to the shaders. So we need to have the standard view projection matrix. We send that in, and then we just do all our business of arming the 4 color buffers, G0 through to G3 for drawing. Then we just go ahead and draw. With the rooms, I am grabbing all of the planes which are defined in the rooms and lumping the vertices together. So for one room, there's actually a whole bunch of different vertices stuck together. So I'm only doing one draw call to draw an entire room, which is good because draw calls are expensive. When we go to the ray tracing stuff, we would have to grab all of our planes, all of our spheres, and sort of flash them over in one go in the data image, just like we were doing before. So we would go ahead and do this, but what I found was it was really slow. It was really slow. Let me just sort of to give an idea for how we can speed this up. So I've sped this up. It's working a lot better now. As we can see, there's no sphere. And that makes sense because the sphere at the moment is not being handled by the deferred shading. That's being handled. The ray tracing is being done by the rasterizer, which does not at the moment take the sphere into account. It's actually not too hard. We just make a sphere model in Blender, draw it at this position with this color and size. That's easy. I've been too lazy to do that. It is doing the shadow. It's doing that pretty well. And then what are we doing here? Yep, look over here. We have the same sort of lighting and shadow calculation as before. And we start to realize the purpose of defining objects on the Raytracer. The purpose of defining an object on the Raytracer, the point is not to be visible anymore. The point is to define where the things are that block shadows. So if I don't define an object in my Raytracer, that's perfectly fine. It just won't cast shadow. So then, obviously, the question is, how can we sort of calculate which things are going to cast shadows and which aren't? And for that, I'll just sketch up a quick little level. Okay, so let's say I have, let me just do this. Okay, let's say I have this situation. These are my walls. These walls here could not possibly cast any shadows on things. They can have shadows cast on them. That's being handled by the lighting calculation. But say I have a light. There's no point checking the light against all these walls, which are obviously not going to cast shadows. This is what we call convex geometry. Convex geometry, it's sort of like if you took a rubber band and stretched it around this shape, it would fit to it. On the other hand, this part is concave geometry. Concave geometry is, well, if you stuck a rubber band around here, there'd be space. It wouldn't work. And it's this concave geometry that could potentially cause shadows. So a naive approach is we take a point and we look at a neighborhood of the point. So these ones here. And we can determine, hey, based on the fact that these two points here are filled up with walls and this point isn't, that indicates that this point here is concave. And this point here should be casting shadows. So we won't load these planes into the shader. We'll just load this plane into the shader. And that works. Like, let's say our light is over here. It will pretty much cast the shadow as it's supposed to. But the issue is we don't know how big this piece is. So light can still sort of come through here, and that's bad. So another approach we can take is we can sort of scan. So we can go, okay, let's scan horizontally left to right. We'll go across here. These points are all joined. So we'll call that an edge. These points are all joined, so we'll call that an edge. And then we'll go vertically. There's an edge there, an edge there, and an edge there. And then we say, okay, given that we have this set of edges, we can detect how they're sort of joined together and check whether at each corner it's convex or concave. And as we can see here, the test for being concave is that the angle is bigger than 90 degrees. Actually, bigger than 180 is the mathematical test. And then the question is, well, how do we determine that? Well, think about the right-hand rule. So if we imagine sort of going around here, and just imagine the normals of each of these walls. So clearly this point is north, west, south, yeah, south, and east. Okay, so here we can see, okay, if we have a way, as we do this, the direction that we run actually matters. So if we run right to left, right to left, yeah, that's right. If we run right to left, then that's a south wall. If we run left to right, that's a north wall, and so on. So this will be a west wall, and this will be an east wall. East. And we could say, well, how do we know which way we're running for each of these? Simple case is the geometry lumper actually already calculates that. So what it does is it says, okay, well, if we have free space up here, then there should actually be a north and a south wall defined here. Okay, trick question. But if this space is filled up, then the only free space is down here, and so this will be a south wall. Anyway, have another look at the geometry lumper for more details on how that works. But looking at this right-hand diagram situation, we can see that if a west edge connects to a south edge, then that is convex. If a south edge connects to an east edge, then that's convex. A north edge will have to connect to a west edge to be convex. But here, this north edge is connecting to an east edge. So both of the edges which are involved in that connection are marked as concave, and both of these walls can cast light. Because, for instance, if I have a light over here, I want this east wall to kind of block that light and cause shadows going back, if that makes sense. Anyway, so as always, I mean, there's a lot of things that I sort of glossed over, a lot of sort of umming and ahhing, but I didn't want to make a 4-hour video, so I gave a very brief overview of it. Yeah, as usual, check the code. Let me know if you have any questions. But yeah, it's actually pretty trivial to add the spheres back in. This is running at a good frame rate, and it looks nice. So just for comparison, I like this shot. Just for comparison, this is what it looks like now after the optimizations. And the frame rate it's running at is pretty good. Versus what it was looking like before. And again, you know, note that frame rate, that's pretty important, and the level of detail that we can get into the frame is limited as well. Unless you like this look. I mean, it's not the worst look. But anyway, hopefully you can sort of see the dramatic difference. And with that being said, I'm probably going to leave the ray tracing for a little bit because it's been a lot of late nights getting this stuff to work. I'm going to look at some other stuff for the time being, unless you have any requests. Anyway, all the best. I hope you enjoyed this, and yeah, see you again soon. Bye.